In part one of our systems of linear equations in two variables, we looked at solving linear equations using graphing. In part two, we're going to look at how to solve these linear equations in two variables using substitution and using addition. Okay? I think the graphing method, obviously as long as you have a graphing calculator, is a fairly nice method. But as I said, it does require a graphing calculator, or it does require some graphing. And you won't always have, the graph won't always give you the exact answer on the graphing calculator, depending upon what the answer is. So these two methods will do that for you. Okay, first by substitution. Solving a linear system by substitution. It is how it sounds. You're going to come up with one of the two equations is going to be an x equals or y equals equation, and you're going to substitute what x equals or what y equals into the other equation, and you're going to have one equation and one unknown. So our steps, as necessary, step one, solve one of the equations for one of the variables. Whichever is easiest, whichever avoids fractions, for example, you want to solve for that variable. Step two, substitute the expression you found in step one into the other equation. This will create a new equation in one unknown. And as you know, you can solve one equation in one unknown using our fairly basic algebra. Step three, we're going to solve this new equation. Step four, we're going to substitute our solution, x equals or y equals, into the equation from step one, and we're going to find the value of the remaining variable. And then step five, we're going to check our proposed solution, and we're going to check it in our original equations. Just like we did with our graphing, we want to check it in our original equations in case we made a mistake solving for one of the variables or substituting. Okay, let's take a look here. Okay, so let's take a look. So I think I have enough space on this paper. Solve by substitution. And my two equations are going to be y equals 3x minus 7. And the second equation will be 5x minus 2y equals 8. All right, so equation one, the first equation here you can see is in slope-intercept form. The slope is positive 3 over 1, and the y-intercept is negative 7. My second equation here is in standard form, ax, by, and c, where a is positive 5, b is negative 2, and c is 8. Now with our graphing method, equation one is already good to go into the calculator. We could solve equation 2 for y, put both of those into our calculator, find the point of intersection if indeed they intersect, and we'd be done. We're going to do substitution this time, and as you can see, step one is already done for us. Step one is saying solve one of these equations for one of the variables. Well, that's been done. This equation is solved for y equals. So that means we can simply substitute what y equals into the second equation for y. All right, so step two. I'm going to write the second equation, 5x minus 2, and where I see y, I'm going to substitute what y equals. Y equals 3x minus 7. So there's the reason it's called substitution. And I have a new equation. And this new equation is in one unknown. X, it has only x's, there are no longer any y's. Okay, so step 3 says, let's solve this new equation, in this case for x. So first I'm going to distribute -2, and it may help you to circle these three things with their signs. So this is a -2 and this is a -7. That's what students lose. And if you want to draw some arrows, that might help you as well. -2 times 3x is -6x. -2 times -7 is +14. And I get 8 over on the right side still. I can now combine like terms. 5x minus 6x is -x plus 14. I subtract 14 from both sides. Whoops. To isolate the x, I have -x equals 8 minus 14 is -6. Feel free to use a calculator for that. It's a calculation. And then I divide both sides by -1 because I don't want -x, I want x. And I have x equals 6. So this whole piece right here is step 3. Solve the new equation. Okay, step 4. Take our 6 and let's substitute that into the equation from step 1, which was this one. So I know, oh, well, y is equal to 3x minus 7. So if I know what x is, I can substitute it. And I always want to use parentheses when I substitute. And then again, this is a calculation. If you need a calculator, help yourself. Mentally, 3 times 6 is 18. 18 minus 7 is 11. So this is step 4. Okay, substitute. So my proposed solution. So my solution is, I think, I haven't checked it yet. My solution is, I think, 611, the point 611. So I think these two lines intersect. And I think they intersect at the point 611. Okay, step 5, is check it. And again, we want to check in our original equations. If I made a mistake, if I put this in incorrectly, then my work will be incorrect here. I'll have an incorrect x. If I put this in here correctly, I'll have an incorrect x and a y that works with it, but it's not correct. So I could have made some mistakes along the way. So I want to check my originals. So here's my equation 1. My equation 1, it says y equals 3x minus 7, so I think y is 11. Again, I always use parentheses to substitute. That way I don't misplace negatives if they happen to come along, or I don't make mistakes with multiplication or addition. Does 11 equal 3 times 6 minus 7? Of course, that's a question. And the left side is 11, and the right side, again, with the calculator or mentally, 3 times 6 is 18 minus 7 is 11. Well, equation 1 worked with my 2 points. Let's try equation 2. I'm going to substitute. Again, I'm going to replace the letters first with parentheses and then put the variable inside. 5 times x is 5 times 6, 6 in the parentheses. 5x minus 2 times y, y is 11. Does that, question mark, does that equal 8? So here's my second equation. I've got it down here. I've substituted in using parentheses for the letters, and then I put the value of what I think is true. This side, again, I can do this mentally, but you can use a calculator. 5 times 6 is 30. 2 times 11 is 22. 30 minus 22 is 8. And that one checks out as well. So the solution that I thought was correct is indeed correct. Okay, I'm going to start you on another example so you can see how see another possibility for this. Get my paper straightened out here. Okay, so let's solve this one by substitution. And we're going to solve this system. It's going to be 5x minus 4y equals 9. And this second equation is going to be x minus 2y equals negative 3. Okay. Now you'll notice here that neither one of these is an x equals or a y equals. And in order to do substitution, we need to be able to put whatever x is equal to into the other equation, or whatever y is equal to into the other equation. Now, my recommendation is to avoid anything that results in fractions. So for example, if I were to look at the first equation, solving for y or solving for x is going to result in a fraction, and maybe more than one. Okay, and working with fractions is an area that most students struggle with, and it's an area that everybody struggles with. If I look at the second equation, if I solve for y, I'm going to have to divide by negative 2. I'm going to have fractions. But if I solve for x, that just means I add 2y to both sides, and I don't have fractions. So my recommendation were to be to take this one and solve it for x. So x minus 2y equals negative 3. Well, whoops. If I add 2y to both sides, I have x equals, and it's your choice, I'm going to write 2y minus 3, but you could write negative 3 plus 2y. I have x equals 2y minus 3. No fractions. And now I can follow through with the rest of what we just did. I can substitute this expression in for x in the first equation, and I'll have two y's. I'll have one equation and all y's. And I can solve that for y and then go back and check for x, etc. I'm not going to do it. I'm going to tell you the solution is the point 0.54. These two lines intersect at the point 0.54. If you'd like to do the work, I'd recommend it and see if you can come up with a solution of 0.54. All right. Now let's talk about solving linear systems by addition. All right, how do we solve linear systems by addition? All right, I'm going to use a piece of scrap paper and just kind of show you what's behind all of this on my scrap paper. We know the following. We know that if we have any equation, I'm just going to make one up. 3x plus 2y plus 6 equals 7x minus 8. I'll make this an x2. And I would, you don't need to write any of this down. This just gives you a sense. Well, that doesn't make any sense. Let's just, I'm making one up, and I'm making one up that's too complicated. Let's keep it simple. 3x plus 6. Okay. We know if we have an equation and we want to work with the equation, as long as we do the same thing to both sides, it's still an equation. Okay? So, if I choose, I could add 10 to both sides. And I'm not working towards solving it in this case, but this will not change the fact that it's still an equation. If I want, I can multiply both sides by negative 4, and I'll use a little x here for multiplication. Again, if I multiply both sides by the same thing, it doesn't change the fact that it's an equation. As long as I do the same thing to both sides, it doesn't change as an equation. Now let's say that I told you that x equals 7. Well, if these two things are equal, then I can add x to one side and I can add 7 to the other side. And again, I've not changed the fact that this is an equation. Because x and 7 are the same thing, I can add the x to one side, the 7 to the other, and my equation is still an equation. if I say that one side is 2x and the other side is x plus, if I tell you that 2x equals x plus 8, okay, if these two things are the same, then I can add 2x to one side, and I can add, and I'll put it in parentheses just to keep it a little cleaner looking, and I can add x plus 8 to the other side, and again, I don't change the fact that it's an equation. So it may look a little strange, and it doesn't make a lot of sense for this problem, but no matter what I do, I can add the same thing to both sides, and if the same thing doesn't look the same, but I've told you it's the same, I can still do it. Okay, so let's talk about, we're going to see, I spelled this linear, doesn't make any sense. We're going to see how that comes up in a little bit, but that's to give you some sense of what's going to happen here with doing this addition method. Okay, this method is most useful when both equations are in standard form Standard form is, of course, AX. I'll tell you, I'll put that in parentheses. Standard form is, of course, AX plus BY equals C. X's and Y's on one side of the equal sign, constant on the other, with non-1 coefficients. And I know that's kind of a weird thing to say here. So let's go back and look at these two, which I think are still on my screen. Let me pull it down a little bit. Yes, let's go back and look at these two equations. You'll notice that equation 1 here, the first equation, has a 5 coefficient and a -4 coefficients. Both of those are not 1, so they're non-1 coefficients. You'll notice that in equation 2, x's coefficient is a 1. Y's coefficient is -2. But the coefficient of a 1 and for the x here means that this one is probably better solved using substitution, because it's really easy to go from here to here and then to substitute. From here to here and then to substitute. So we want two equations that have non-1 coefficients in all 4 locations. The first equation's xy and the second equation's xy. Okay, let's jot the steps down here. This is going to take a bit. Make sure my sheet is straight. All right, so the steps for how to do this. And then we're going to talk about how you can add what adding the same thing to both sides means. Okay, my steps. 1. This is kind of a long step. If necessary, but this is the key step to making this work. If necessary, multiply either equation or both equations by appropriate non-zero numbers so that the sum, hence the sum, the reason it's called solving by addition, we're going to talk about getting sums, the sum of the x coefficients or the sum of the y coefficients is 0. Okay, that's a mouthful. There's a lot there. It probably doesn't make, unless you've seen it before, It probably doesn't make a whole lot of sense yet, but we'll go through a couple of examples and we'll see it. Okay, so, and then here's the part. Add the two equations. This is the part I was alluding to when I did my scrap paper work. Okay, I can add the same thing to both sides as long as I know that that what I'm adding to both sides are the same. And they can look different, but if I've told you they're equal, I can add them. I can add them one to one side and the other to the other side. Okay, so add the two equations. The result is one equation in one unknown. And that may look familiar. That was the result from our substitution 2, and that's the goal. We have two equations and two unknowns. We want to get it down to one equation in one unknown so that we can solve it. Okay, step 3, solve this one equation, which we've been doing all along. Step 4, just like with our solving by substitution, we're going to substitute, if I can spell substitute. Substitute, hope that's spelled right. Substitute our solution into either original equation to find the value of the remaining variable and note I use the word original here. If we take our solution, if we substitute it into one of the original equations, as long as we do our math right, that'll save us a step in our check. In step 5, now we're going to check our solution in the other original equation. In the other original equation to see if we're right or not. Okay, so a fair amount here. We're going to come up with a way that we can zero out either the x coefficients or the y coefficients when we do addition. We're going to do that addition, and they're going to zero out, and we're going to have one equation and one unknown. That equation we can solve. We've been doing that all along. We're then going to say, okay, I've got a solution that says x equals or y equals. I'm going to substitute that one into either one of our original equations to get the value of the other variable. And then we're going to check our solution in the other original equation because we've already kind of done the first one. All right, I'm going to use another piece of paper. I don't have enough space at the bottom here. I'm going to turn it over. I need some room. And we're going to take a look at an example. Just a second. All right. Okay, I'll take a look at a couple of examples. All right, solve by addition. Okay, my two equations are going to be 3x plus 2y equals 48. I'm just going to put a 1 there so we can keep track of it. And 9x minus 8y equals negative 24. I'm going to put a 2 there so I can keep track. All right, so as you'll notice, both of these two equations have non-1 coefficients. There's a 3, a positive 2, a positive 9, and a negative 8. None of those four coefficients are 1. So the addition method is generally the easiest method. If we were to start solving one of these for x or for y, we get fractions, and it would be a mess to use substitution. because we had fractions to deal with. We could solve both of them for y without too much difficulty. We're still going to get fractions, but then we'd have to have a graphing calculator with us to graph them and see and get the answer. So, okay, so let's start off with our step 1 here. So I'm going to rewrite my two equations so that I can do step 1 in a way that makes sense for you and your notes. Okay, the goal here is to multiply one equation or both equations so that I have opposite x coefficients or y coefficients. Okay, because then I can add and they'll zero out. So it'd be nice if this were, for example, if this coefficient were -9, well, -9 plus +9 is 0. I would zero out my x's. If this coefficient were -4, were positive, if this coefficient, were +8, +8 and -8 would zero out the y variable. So I'm going to choose to multiply my top equation, and I'll write down multiply this time. I'm going to choose, let's see if I can make it so we can kind of read it. I'm going to choose to multiply my top equation by +4. Okay, my top equation now becomes, whoops, I want to put in my curly bracket again just because. My top equation now becomes, well, +4 times +3x is +12x. +4 times +2x is +8y. And +4 times 98. I have no idea what 4 times 98 is. 4 times 48, 48 times 4, 192 is 192. So I multiplied everything on both sides by 4. My equation is still an equation. And I'm going to leave this one alone, so no change. I'm just going to copy it. 9x minus 8y equals -24. Okay, now here's the part. You'll notice I have a 0 when I add. If I add these two equations, I zero out my y's. But here's what I was saying before. I told you as long as I add the same thing to both sides, I don't change the equal sign. Well, I'm told that this equals this. So I'm going to add this to the left and this to the right. They're the same thing. I can add them. Well, this is great because this zeroes that out. +8 and -8, +8y and -8y is 0. 12x's and 9x's is 21x's. And 192 minus 24, 192 minus 24 is 168. Now I can divide, I'm solving for x, I'll divide both sides by 21, and my x looks to be 168 divided by 21. I got 8. So I think x is 8. Okay, I'm going to choose to put this into equation 1. So here is equation number 1. I'm going to copy the original. I'm not going to copy what I did here. I'm going to put it in the original equation. And I'm going to see what comes out. So I know that x is, I think x is 8. I'm going to find y. Everywhere I say x, I'm going to put in parentheses and then put in my 8 plus 2 times y. So this is equation number 1. I can now solve for y. 3 times 8 is 24. Okay, let's subtract 24 from both sides. Again, I can do the same thing to both sides. 2y is equal to 48 minus 24. I can do that. Divide both sides by 2, and I have y equals 12. So I know that in my first equation, the point 8, 12 makes it true. I just put 8 in there and I got 12 out. So that's kind kind of a first check for equation 1. Now, what I think here is my solution is, again, I think my solution is 812. I think these two lines intersect in one point, and I think they intersect at the point 812. Now, I've already checked 812 in equation 1 because I used 8 and I got 12 out. I'm going to trust my math. I can recheck it if I need to, but I think I'm pretty fine with that one. So my check is really going to be mostly about equation 2. Okay, equation 2 says 9 times x, so I replace the x with parentheses. I think x is 8, minus 8 times y. So I replace y with parentheses. I'm thinking y is 12. Do I get negative 24? Okay, for me that's a calculator problem. 9 times 8 minus 8 times 12. Whoops. And let's close my parenthesis. And I came up with negative 24. So I got negative 24 on the left. And that's equal to negative 24 on the right. And so I think my solution of 812 is correct. Okay, let me show you another. These can get slightly more complicated. So let's take a look at one, get you started on one that is slightly more complicated. So this example is going to be solve by addition. Okay, and my two equations, I have 7x plus 2y equals 5, and I have 2x plus 3y equals 16. Okay, you'll notice again, a key thing that tells me that solving by addition makes the most sense is when I have all non-1 coefficients. My coefficients are positive 7, positive 2, positive 2, and positive 3. So let's write them over here so we can do some multiplying. 7x plus 2y equals 5, and 2x plus 3y equals 16. Now you'll notice I can't just multiply one of these equations by a number and make it so that it matches up with the second one. So I'm going to have to multiply both equations by numbers to give me the same coefficient or opposite coefficients for either the x's or the y's. Okay, again, let's look up here again. Up here at the very top up here where I'm showing you, I saw clearly that 3 times negative 3, 3 was a factor of 9. So I can multiply the top equation by negative 3 and I could zero out my x's. Or 2 is a factor of 8. So I can multiply my top equation by positive 4 and I would zero out my y's, which is what I chose to do. Here, 7 and 2 they're not, 7 is not a factor of 2, 2 is not a factor of 7, and 2 and 3 aren't factors of one another, or 1 is not a factor of the other. So I'm going to have to figure out which one of these variables I want to get rid of, and I'm going to multiply them both by something. So let's think for a second. Okay, let's think for a second. The lowest common multiple of 7 and 2 is 14. So if I multiply my top equation by 2, my bottom equation by 7, or one of them have to be by negative. The top equation by 2 or negative 2, the bottom equation by the opposite, 7 or negative 7, I would get a 14 and a negative 14 here. That's one possibility. That would zero the x's out. This one has, as a lowest common multiple, 6. 2 goes into 6 3 times, 3 goes into 6 2 times. I like that better. I would rather multiply by things by 2 and 3 than by 7 and 2, because I think 7's probably, I can probably do 3 in my head or 2 in my head. I probably can't do 7 in my head. I'm going to multiply the top one times 3. Multiply the bottom one times negative 2. Remember, I want them to be opposites so that I can add and zero them out. So the top equation by 3 gives me, again, let me put in my brackets, 7 times 3 is 21x, positive 2y times 3 is positive 6y, and 5 times 3 is 15. Multiplied everything on both sides by 3, and this equation is still an equation. Okay, I'm going to multiply everything on both sides by negative 2. 2x times negative 2 is negative 4x. Okay. Positive 3y times negative 2 is negative 6y. And there's my 0. I wanted opposite. You know, I wanted opposite coefficients, so when I added, that would zero out. And 16 times negative 2 is negative 32. Okay, so now you're on running. Now you can add both equations. This side will give you, I think, 21 and negative 4 is 17. And I'm not sure what 15 and negative 32 is. 15 minus 32. Oh, that works just fine. Okay, I would check, you can go from here, give it a shot. The solution is negative 1 comma 6. So I'm telling you that these two lines intersect at one point, and that point is the point negative 1, 6. Okay, one more thing to take a look at here. What happens? We've talked a lot about problems that every single one of our solutions so far, every single one of our systems of two equations has had one solution. They've all been intersecting lines. Okay, so what does it look like if two lines are parallel or two lines are the same line, one on top of the other? So what does it look like to have no solutions or infinite solutions? How will I know if that's the case? Now with graphing, this is pretty simple. With graphing, you're going to see two lines that are parallel, or you're going to see one line get graphed on top of the other line. So graphing, it's a pretty simple thing to figure out. It's not quite as straightforward if you use addition or substitution. So let's take a look first, and I'm just going to say solve. I'm going to do this. I'm going to do two more so we can see this. We're going to say solve 4x plus 6y equals 12. The system, and 6x plus 9y equals 12. Okay? So I look here and I see, okay. Now you could solve both of these for y, and they both have to be the same thing. And you can see how they turn out, and that would be graphing. I look at this and I see 4 non-1 coefficients, so I'm thinking addition. Now, 4 is not a factor of 6, 6 is not a factor of 9, so I'm going to have to multiply the first one and the second one by something to get a lowest common multiple, so that I get either the x's to be opposites or the y's to be opposites. Okay, so let's see. I'm going to copy them again. Okay, so I'm going to multiply the top, and I'm going to work, I think, with the 4 and the 6. And their lowest common multiple is 12. So I'm going to multiply my top equation by positive 3 And I'm going to multiply my second equation by -2 because I want them to be 12 and -12. Okay, so here I come. Positive 3 times 4x is 12x. Positive 3 times 6y is 18y. And positive 3 times 12 is 36. Okay, -2 times 6x is -12x. Hey, great. There's a 0 I'm looking for. -2 times positive 9 is -18y. Wait a second. -2 times 12 is -24. Wait a minute. These are also opposites. So when I go to do my addition, I wind up with 0 equals 12. Well, that doesn't make any sense. That's never true. 0 doesn't equal 12. So this tells me when I see something like 0 equals 12, this is never true. 0 never equals 12. Okay, so this tells me, so there are no solutions. Okay, in other words, these lines are parallel. There are no solutions. The lines must never touch if there are no solutions. So that's what you'll often see. That's what you'll always see if there are no solutions and you're doing the math. You're going to come up with an equation, an equal sign that makes no sense. 0 doesn't equal 12. And that should tell you, oh, there are no solutions here. Unless I did something wrong in my math, of course. But this is telling me my math is correct, that there are no solutions to this. Okay, so what does it look like when there are an infinite number of solutions? Okay, last example. Let's solve this one. And my linear system is going to be y equals 3x minus 2 and 15x minus 5y equals 10. All right, in this case, I have a y equals something. One of these is in slope-intercept form and one of these in standard form. This one's ready for substitution because it's already solved. The first equation is already solved for an unknown. It's already solved for y, so I can just substitute. So this one looks like it's really ready for substitution. So let's substitute. I'm going to take the second equation, 15x, and everywhere I see y, I'm going to put in 3x minus 2. So 15x minus 5 times 3x minus 2 is equal to 10. I substituted in for y. I put what it says here that y equals. And then I'm going to distribute. And again, here's where I might want to consider circling my pieces here, because this is where students lose negatives. -5 times positive 3x is -15x. -5 times -2 is positive 10. And you'll notice, as I combine like terms, I come up with 10 equals 10. And now wait a second. This is always true. What do you mean 10 equals? Of course 10 equals 10. Okay, so just like the one up here, this was never true, therefore there were no solutions. This is always true. Okay, therefore there are an infinite number of solutions. 10 equals 10 is always true. Okay, so there are an infinite number of solutions. Okay, in other words, these lines are the same line. Okay, so now we've covered all possibilities, how to solve a linear system in 2 variables, graphing, substitution, and addition.